Alright. Let's get going here. So, I need your attention. Got some announcements. They're important. Alright, first of all, we're going to finish cells today. And there are quizzes, obviously. When you are using them, hopefully you are gaining some information about how you're studying. What you need to review, what you don't need to review. Where are you in understanding? Those are designed for it. So I'm hoping you're using them. Today in lab and tomorrow in lab, we're going to do a lab over diffusion and osmosis. Hands-on study. But there are also virtual labs on the Connect website. When you purchased your textbooks, you should have gotten the code for McGraw-Hill Connect. That's where these labs are. So when you click on that in the assignments, it should take you to McGraw-Hill, you enter your information, and then you're in class on Connect. If that does not make sense, ask me after class. Okay? So there are 2 assignments currently. There'll be others coming up down the road. The purpose of those is to reinforce further diffusion and osmosis. Okay? They're that critical to understand. That's why I have additional activities for you. Okay? So far, so good? All right. Now, the other half of the announcements is important as well. You have a written exam on Friday, September 15th. You will not be in here. Do not come to this room. You're not going to be able to take the exam if you come to this room. That would be bad. Where you need to go is hard time 258. There's that. Second floor, all the way down there. It's up in the nursing section. So if you're in 201 or 221, just keep going down and turn, and you'll find us. We take exams on computers. Okay? So that's where the computer lab will be. 258. Okay? Now, there are slightly more of you than there are computers. Okay. Because I sent out an announcement, 6 of you have already filled it out. But if you are able to take the exam at 1:50, not at 1 o'clock, I would greatly appreciate some of you coming at 1:50. All right? I know some of you are athletes. That's not going to be possible. Okay, I get it. Some of you have class. I get it. But if I can get about 10 to 20, 20 would be ideal. That'll lessen the number in there at the beginning. Okay? Please and thank you. I already saw something. Work? Answer? Yeah, good. All right. So what that'll do is just give you a little extra time. But not everybody's going to grab that code. But also it'll be fewer people. You can't. It works. Okay? So where are we going to take the exam? 258. All right, what time? 1 for most of you. All right. Any questions? Yes.
What time is the study date? What is it?
Time study group.
Yes.
7. Where?
Tomorrow.
Yeah, where? Yes, tomorrow. Sorry.
Tomorrow
Yes.
at 7. Where?
Tomorrow at 7. Where will it be? Not 201. It's in one of those rooms up here. It's up
Me
in
too.
220. So you get to that on the ballot side. 7 o'clock. All right. Anything else? Yeah.
Do they do it virtually?
I will ask you to. Yes. Or at least record it. Okay. Anything else? Okay. All right. So today, what we're hoping to accomplish is to understand the difference between simple diffusion and osmosis. And with the concept of osmosis, there are three terms: hyper, hypo, isotonic. We're going to talk about movement of water across the membrane in those solutions: hypertonic, hypertonic, isotonic. We're going to talk about the differences between simple diffusion and something called facilitated diffusion. We'll compare that to active transport. And we're going to talk about the idea of ATP, cellular energy. Is it needed for all three processes, two of those processes, one of those processes, and which skips over time? We're going to talk about something called the sodium-potassium pump. And we'll finish up with a little discussion of endocytosis and exocytosis. So that's the course of the day. All right? So that's where we're headed. So again, we have been down here talking about atoms, the built molecules, macromolecules. You are learning about organelles. We are talking about cells. So we defined the cell. Now we're going to start talking about some of the things that go on in a cell. So there's our cell. And what is a cell by definition? The simplest, smallest, structural, functional unit of life. And what is it? This is the year. 100% of you will get that question on the exam.
Yeah.
100%
He wants
of
all
you
of
will
us to
get
get it
that question right. Okay?
What is
So,
that?
what that means is if I look at the cell and I think about something like the organelle, or I think about a mitochondria, those are organelles. They don't exist outside the cell. They cannot exist outside the cell. In other words, the things that build a cell cannot survive outside the cell. That means the cell is the smallest unit of life. And we also talked about the idea that cells give rise to other cells. They can't come from nothing. All organisms are made of cells, or a cell. There are single cell organisms. And the cell is going to dictate the function of the organism. Change the cell, the organism may change the way it functions. These are all concepts about cells. Now, the cell has a border that we call the cell membrane. We'll take a look at that a little bit more. And I gave you a list of structures inside the cell that I would like for you to know. I said I'm not going to give a lot of time to that. I'm just going to allow you to find a very simple definition. But if I want to know where lipids are made, what are you going to tell me? Where are lipids made? Out of that list, who's been studied? Smooth BIOL, smooth endoplasmic reticulum. Lipids are made in smooth endoplasmic reticulum. And which of these would contain enzymes to degrade things, to break things down? Which organelle contains enzymes that will break things down? Lysosome. It's in the name. Lysosome. Lytic. Lyse. Break. Break down. It's in the name. Okay. Lysosome. Breaks things down. And as always, if I say mitochondria, you say powerhouse of the cell. What does it produce? That is this power. ATP. Adenosine triphosphate. That's the energy of the cell. Mitochondria produce it for a eukaryotic cell. A cell that looks like that. Okay. Now, while we were talking last time, we've mentioned some things like these. Okay, these little things here. And those are microvilli. Increase the surface area. We talked about cilia, little hair-like structures. They're not part of the cell membrane, they're outside of the cell. They'll go project from the cell membrane. They move mucus primarily. Talk about a flagella, one single tail-like structure. So we were talking about these types of things on these cells. Now, since we're going to talk about transport today, let's just revisit the idea of the cell membrane. It's described the cell membrane as being made of a special lipid, phospholipid. Recall that the phospholipid has two fatty acid tails and a phosphate group, sometimes referred to as phosphate head. Phosphates are ionized. They are ions, so they need to be near water. And the lipids, we describe lipids, do they like or not like water? They do not. They're on the inside, so it's a bilayer, two layers of lipids pointing inwards, and their heads outside. And that creates a hydrophilic outside of the membrane, both outside the cell and inside the cell where water is present. And the middle is lipids. The middle is lipids. Hydrophobic. So we have to figure out how to move molecules across this membrane. Because if you are an ion, you can't go through that hydrophobic center, the hydrophobic middle of the membrane. It will not work. If you're too big, you can't get through. Okay? Those are the basic things that are going to block or cause whether things move through or not. So, we describe the membrane as selectively permeable. Permeability, big word, permeability, is a measurement or a description of how easily things go through. The door standing wide open like that, the room is now permeable. Everybody can go through. Okay. But if I close the doors and I lock the doors, the only way you can get through is if you have a key. It is now selectively permeable. Only certain things can go through. That's the concept of selective permeability. Now, cell membranes usually are never said to be impermeable, where nothing goes through. It just contrasts selective versus other ideas. So the plasma membrane can be thought of as both a barrier blocking things and also a gateway. You get through it. You get through it to meet certain criteria. Now, one of the ways that we move things through a cell membrane is by filtration. Filtration. And this has to do with pressure. Hydrostatic pressure. Pushing it through, so force, because of hydrostatic pressure. Now, in our bodies, that hydrostatic pressure will primarily be blood pressure. We'll get to that next semester. And that's going to be the force. So in this demonstration, we're showing things moving through openings in the cell. So, I asked this question: what organ do you think of that would do filtration? Filtering all the time. Right? Gotta get it out the waste. Gotta get things that we don't want out. The liver does some filtration. Lymph nodes do some filtration. But the kidney's the one that we almost always think about for filtration. Force molecules through a membrane because of blood pressure. That's what the kidney does. All right. So that's the first one. Second one is simple diffusion. Simple diffusion. Now, in simple diffusion, molecules are going to move what is said to be down their concentration gradients. In other words, from high to low concentration. Where is it more concentrated? It's going to move to where it's less concentrated. And our demonstration here, our diagram is indicating that. Here's our lipid bilayer, our plasma membrane. We have molecules on the outside, and we're theorizing these molecules can cross the membrane. So over time, they start to diffuse. They start to move across. Why are they moving across? Because they bump into each other. Those of you who care, that's called Brownian motion. So they bump into each other, and they start to move around. And as they move, it's like billiard balls on a pool table. Out they go. And some of them move through the membrane. That's just random. That's what they're doing. And they're moving from where they're in concentration to where they're not. Until what happens? So they're in equal concentration. Okay. Now, when they reach equilibrium, when they're equally concentrated on both sides of the membrane, does that mean the molecules have stopped moving? Still moving, still bumping into each other, but for every one that goes through, one goes the other way, staying in equal concentration. So far, so good. Beautiful, brilliant concept. Means I can draw blood in my arm, I can draw blood in my leg. Sodium concentration better be equal in both places. Diffusion. Spread out through my blood. So it's equal. That's the idea. Now, there are things that affect how quickly it moves. One is temperature. You increase the temperature, diffusion happens more rapidly. Okay. Converse is true. Lower the temperature, things don't move as fast. Surface area. We have more membrane, then we're going to have more diffusion. Why do we have microvilli that line your intestinal cells? More diffusion. More things to move across. With more surface area. Flatten the cell out, take away the membrane or the microvilli, things don't move as quickly. Take out a section of the intestine, less things are going to be absorbed. Permeability, we've already talked about that. The membrane is more permeable, and more things can diffuse across. Close the doors. Like back when my boys were little, couldn't get through those doors. They were too heavy. So, that's changing permeability. Steepness is a gradient. How many snow skiers do we have for snowboarding? Just one person. Wow. Bunny slope versus a black diamond, right? Green bunny slope like that. Black diamond like that. Which one do you go faster on, right? Unless it's full of ovals and then I'm bouncing and billiard ball down the slope. If it is a steeper gradient, if it is more concentrated on one side than the other, diffusion occurs. You increase that difference, it goes faster. Molecular weight. Small molecules move faster than big molecules. Small molecules move faster than big molecules. Guess what? We're going to demonstrate that in lab today. Those of you from yesterday, you got that idea. I hope. Demonstrated it. We have two different molecules. One diffused, the other didn't. Based on molecular weight. All right, so that's our idea about simple diffusion. And it's the basics for what we're going to move on and talk about now. Things move from high to low. That's the base idea. And then we can change some conditions. Excuse me about that. All right. So what else? Osmosis. When I say osmosis, sometimes I watch people and they just go, I don't like that idea. Well, that tells me something. Aggressive with it a little bit, which is good. Osmosis is diffusion. It's nothing different than diffusion. All we're doing is talking about a specific molecule. We're not talking about diffusion in a general sense. We're talking about diffusion of a specific molecule. Which one? Water. And the way we define it, if we do the technical definition, movement of water across a selectively permeable membrane. And water moves from high concentration of water to low concentration of water. That's where we get all tripped up. I am not saying volume. I'm saying concentration. Difference. If I am describing this, I am saying I have a membrane. If I have 1% on this side and 10% on this side of a salt solution, where is there more water concentration? Left or right? 1% or 10%? 1%. If the volume's equal, both sides have an equal volume. But 1% salt means how much water? 99. 10% means how much water? 90. Which one has a higher concentration of water? What we need. Now, at the risk of confusing you, I'll say an or. Water moves from low concentration solute to high concentration solute. I didn't change the definition, I just described it. I don't care which one you work with. Pick one or the other, but do not confuse them and blend them together. Then you're in a heap of trouble. Water moves from where it's in high concentration, 99%, where it's in low concentration, 90%. Or water moves from where the solute is low, 1%, to 10%. Same idea. Just stated a little bit. Now, we are saying that this molecule isn't moving, just the water. That's osmosis. We're going to put it into some practical terms here in a minute. So if we compare the two, diffusion, high concentration, low concentration, moves until it's spread out. That's diffusion. Water moves to the low concentration of water. High concentration, low concentration. they are in equal concentration. And notice what happened to the volume. Change. Why? The only thing moving is water. Only the solvent moves. Water. The only thing that moves. So the volume will change if the water moves from high concentration water to low concentration water. Yeah? Okay? Getting there? Seven. Put it in practical terms here. So, when we talk about osmosis, there's this concept of something called osmolarity. Now, if you're a chemist, the term molarity means something to you. It's a measurement. It's a measurement. Measurement of how much matter you have, how many molecules you have. 6.023 times 10 to the 23. Look at that. 451 years later, I still remember. I've used it here. So, what we talk about is osmoles of solvent. Now, what I'm saying is, over here I have 1% and 10%. It's just a different way of describing the amount of solvent. So, why is that important? Well, here's an example. If I say osmole means 1 mole of dissolved particles, 1 unit of dissolved particles. I'm not worried about a mole. A blind animal that digs in the dirt. I'm not worried about that. What I want you to understand is it's a unit. It's a way to measure. So if I have 1 unit of glucose in 1 liter of water, I have 1 osmole. If I have 1 mole of sodium chloride in 1 liter of water, I have 2 osmoles. The difference. Why 2 for sodium chloride and 1 glucose? Yeah, I know, it's so crazy. Why 2 versus 1? Yeah. Well, yes, but why is sodium chloride 2? Keep going. You're on the right track. What does sodium chloride do when it goes into water? Dissolves, but it dissolves and becomes what? 2 what? Am I hearing it? There we go, ions. 2 ions. It's no longer 1 molecule held together. We saying it over here, sorry. If it's no longer 1, it splits apart. Remember, they're ions when they enter the water. So they break apart. So 1 becomes 2. Whereas glucose, because it's covalently bonded, stays together. Doesn't break apart. Okay? So that's the difference. Now, right now you're going, why is this important? Well, here's why. Because when we measure the amount of things dissolved in your blood, or in the fluid around your cells, or the fluid inside the cells, they are all approximately 300 of these units, milli-units. And what does that mean? It means that when I want to give you an IV solution, it's 0.9% saline. 0.9% saline equals 300 milliosmolar. Am I giving you more solute when I give you 0.9% than what's in your body? No. Giving you the same. Or it's Ringer's lactate, if you have ever heard that term. It's all the same. They all are equal. And so if you go into the hospital, visit somebody, or you have to have an IV, they hang a bag with 0.9% saline. Unless there's something really wrong, and then they're going to do something different. So this is a big idea about how much stuff is dissolved. Why is this critical? Well, it goes with this idea. The ability of the solute to affect the volume and pressure inside a cell. So the amount of solute, I need to know that because it's going to cause an adjustment to volume potentially. And pressure inside of the cell. And that's huge. So, we start talking about these terms that sometimes give you the heebie-jeebies. Hypo means what? Below or less than. So a hypotonic solution has less permeating solute. It looks like that. No, it's a little small for the back of the room, but I'll blow it up here again. So the green is the solute. The solution around the cell has less solute. So over there, 1% or 10%, which one is hypotonic? So if there's a hypo, then there's a hyper. More permeating solution when you compare it to the cell. So it looks like this. More solute out here than compared to inside. Solute cannot cross the membrane, only water. That's what we're saying here. So then we have hypo, hyper, we have iso. Fill in the blank. Equal or the same. There is no difference in the concentration of solute inside and outside of the cell. So the artist drew it. 5 inside, outside. 6, whatever. 6 and 6, whatever. I can't count. Equal. The same. Okay. So we've defined hyper, iso. What does that mean? Wait, why do I care? Why I care. Cell in a hypotonic solution, what's it going to do? Expand, contract, or stay the same inside? Contract, stay the same, expand. What's it going to do? The cell is in a hypotonic solution. In other words, which way is the water going to move? Into the cell or out of the cell or not at all? Oh, I'm hearing in and out. That's a burger. I don't want the burger. I want an answer. In or out? In. Why? Where there's more solute? Inside or outside? Inside the cell. Where is the water concentration greater? Inside or outside of the cell? Outside of the cell. There's a greater water concentration. Which way will water move? into the cell. You there yet? You slowly making sense? Cell in a hypertonic solution. Which way will the water move? Into the cell or out of the cell? Will the cell expand or contract or stay the same? Which way will it move? Out. More solute outside the cell. Less water concentration outside the cell. Less solute inside the cell. Greater water concentration inside the cell. Water moves to where there is lower water concentration. So what will that cell do? Shrink. And the hypo would expand. So isotonic, what's the cell going to do? Stay the same.
Yes.
Why do I get 0.9% saline solution? I don't want cells expanding or contracting. Now, very, very sad situation. You, a nurse, down the block from us, couldn't read the doctor's orders clearly or misunderstood them or something. Give a patient a hypotonic solution, a hypotonic solution. Patient got it. What happened to that patient's red blood cells? Popped. Yikes. Not good. 0.9% is isotonic. 0.09, hypotonic. 1.9, hypertonic. We use those solutions or variations sometimes. 0.9% isotonic. Equal movement of water.
Yes.
All right.
That's how you know he trusts me.
So we talked about simple diffusion, the movement from a high concentration to a low concentration.
It's just
And we talked about if you heat it up, things move faster. Steeper concentration difference, things move faster. Specifically talked about water moving across the membrane. That's osmosis. But what if the molecule cannot move across by simple diffusion? Because it's too big. Or it's charged, an ion. What then? Remember all those proteins that we talked about that are in the membrane? And we said some of those are going to act as carriers. That's what we're describing here. Carrier-mediated transport. This is the big concept. The bigger idea. So instead of simple diffusion where it just moves through the membrane because it can move across the membrane, we're now saying things have to have some help across the membrane. So again, when I said about the doors, when the boys were little, I'd have to open the door for them. I'd have to help them across the door. I was the carrier. Sometimes they were on my back. So that's what we're describing. Something to help. A protein, that's the carrier, finds a particle. Any particle? Nope. Specific. Just like with enzymes. Now, there's an idea here called saturation. I have 100 carriers. How many molecules can I bind at once to move? 100. If I have 1,000 molecules to move, can I move them all at once? Nope. I only can move 100 at a time. Saturation. Now, one of the specific kinds of carrier-mediated is called facilitating. And that's when we are moving particles down concentration gradient. So it's just like simple diffusion, but we're putting in the helper to help us get these molecules move. We have a carrier to help with the movement, but it still moves from high concentration to low concentration. And no ATP is used. How does it do this? Because when something binds to a protein changes shape. In this case, it carries it from one side to the other. It looks like that. So there's our great concentration and very little concentration. There's the binding site. Whoop. Protein changes shape. The molecule moves in. Just like an enzyme, it's ready to go again. When I say saturation, that's what I'm describing. It can only carry until it is saturated. Why is that important? We'll get to the idea of diabetes. Glucose as a carrier in the kidney. When it reaches saturation, then glucose cannot be transported out of the forming urine. It stays in the urine. Then you have glucose in the urine when you shouldn't, because it's saturated. Too much glucose in the blood to all be carried across. Get fat there for a second. Okay? So that's where it's going to come into play. All right. So that's facilitated. And we said there was no energy involved. Well, if there's no energy involved in facilitated, then there's probably the opposite, where energy is involved. And that's active transport. Sounds the same. There's a protein-specific particle. Protein changes shape. Particle release. Sounds the same. What's different? Phosphorylation from ATP. The energy is used. Bolded it. Gosh, and italicized it to make even more emphasis. ATP. Now, why do I need to have ATP? Because I am moving against concentration gradient. Where's it in low concentration? Outside. Where's it getting moved? Inside. What's on the inside? A greater concentration. All right, my skier can tell us, you're at the top of the hill, what helps you get down the hill? Gravity, right? Steepness of the hill. You get to the bottom, you want to do it again, what do? You want what? Go on the ski lift. Does the ski lift just work, or is there energy involved? There's energy involved. You get back up the hill, we got to put some energy in. Ski slope, yeah, that thing. Ski slope makes sense to you, but you've never been skiing, I don't know. Your Prometheus, you gotta push that thing up the hill, and it rolls down. You gotta push it back up the hill, and it rolls down. Spend the time to do it. Energy involved to go up. That's the idea, or against. Okay? Now, if we compare, notice that we have diffusion and facilitated diffusion, always from high to low. Active from low to high. And we have to have energy. That's the difference. Now, there is a specific active transport we want to talk about for a minute, and that is called the sodium-potassium pump. So, The sodium potassium pump requires an ATP to move 3 sodiums. Where's my sodium? Yellow ones, orange ones, whatever color that is. To move 3 of those out of the cell and to bring 2 potassiums into the cell. That's what it's doing. Moving the sodiums out, potassiums in. So where is there a high concentration of sodium? Outside or inside? Outside. Where is there a high potassium concentration? Inside. Why do I care? If that isn't the case, then your nerves don't conduct, your muscles don't contract, your heart doesn't pump, and you're called dead. This idea establishing sodium out, potassium in, is going to cause our nerves to conduct electricity. It's going to cause our muscles to contract. It's going to cause our heart to beat and pump blood. It's going to cause your diaphragm to contract and move air. All those things. Wow. Might be a big idea. Okay. So, it maintains high concentration of potassium and low sodium concentration inside the cell. Or high sodium and low potassium outside the cell. Now, why do we have this? It is to regulate the volume of the cell. Remember osmosis? We need to establish sodium out and potassium in so that we don't have movement of water. We're going to use it as a secondary active transporter. So that we can move glucose in the kidneys and the small intestine. Just talked about that. Okay? So it looks like that. Here's the sodium potassium pump down here. It's moving sodium out of the cell into the body. So what does that mean for sodium? It's in low concentration. I eat some food. I have glucose. I need to get that into the cell so I can get it back into my body. Glucose moves through this transporter. With what? Sodium. Why can sodium move? Because it's being pumped out. It's always in low concentration inside the cell. Why I like salt on my chocolate like this. Now the other reason is to maintain what's called the membrane potential. It separates charges. Sodium on the outside creates a positive charge outside the cell, and we have a negative charge on the inside. Why? Because we have all these big negative charged molecules. Proteins, DNA, RNA. That's what we're going to use to cause our muscles to contract. And it's for heat production. You guys sitting here right now, I know it's a little chilly. About 15 to 20% of your body's heat is coming because of the sodium potassium. Therefore, you're using calories to stay warm. Okay? No more sweat. Stay chilly. All right. Now, I know I ran out of the bulk transport, but it's pretty self-explanatory.